Good afternoon. Welcome to lecture 61 and 62 on thermodynamics of materials. We, we are solving problems. So problem 6, it was actually problem 6 where we are considering, and we found all partial pressure except pH2S. I will repeat this part. See, follow this. See, P oxygen was found, P sulfur found, P zinc found. These three, I'm sorry, P zinc and P sulfur found. Only pH2S was actually to be found. So for this, if consider this, okay, what I said, if follow press. Consider this simple equilibrium. Hydrogen plus sulfur half H2 goes to H2S, and delta G0 is given here. And so you'll get the equilibrium constant from delta G0 is minus RTLN K. Substitute, write the expression for this at equilibrium pH2S by pH2 power half. Since pH2 and pH2 already known, so no difficulty in finding out pH2S out, and the value is 0.0151 atmosphere. So all four are determined. In this connection, I actually said something alternatively. Many different ways you can find, a number of different ways. So here is an example. So H2S you can find, you don't have to, you may consider, because this is simple and convenient, but you don't have to. You can consider another one. Okay. So like this, zinc sulfide plus hydrogen gas going to zinc vapor and H2S gas. You have to involve H2S, because H2S is to be determined, partial pressure of H2S. But you can make it involved in this way also, provided the partial pressures of other participating gas phase are known, and in fact it is known. For example, if you apply delta G0 equilibrium constant, then the expression is Pzn pH2S, activity zinc sulfide, P hydrogen, and activity of zinc sulfide is 1. Since solid, Pzn is known, pH2 is known, so pH2 can be found out, and same result you will get. So you can actually try this out. Okay? That's for your verification. So because these are all actually mutual equilibrium, they are compatible, all equilibriums. They are in agreement. So anyhow you do. So this I think. Okay. This was and the answer I have listed at the end for your benefit. These are the answers, because these four things. And in the system, what else are there other than this? Already, you know, pH2, hydrogen and moisture, H2, and their values are given at equilibrium. So all four or all six are known now. So can I move on to next problem? It's okay with you? Huh? So problem 7. Problem 7, we actually, let me sketch this. Sorry. Problem 7. $200 of zinc, 200 gram of zinc, liquid zinc, okay, zinc liquid, is placed in a crucible, is placed in a crucible at 1030 Kelvin. On 0 Kelvin. Okay, 2 moles of argon are bubbled through. 2 moles of argon are bubbled through the liquid and the gas comes to equilibrium with the liquid before leaving the system. P total, sometimes I write T means total, is 0.8 atmosphere. How many grams of zinc? Grams of zinc, metallic zinc, metallic metallic zinc remain in the crucible. Remain in the crucible. Question. This question I am giving a reference. This is not Gaskell or Schumann. Okay, I will give the reference. Okay, so this acknowledgement. A. E. Morris. A. E. Morris. H. Morris. Morris. And well, the I will let me write a problem manual. The book actually problem manual. Acha, problem manual for metallurgical thermodynamics. For metallurgical thermodynamics. Thermodynamics. Now, one thing I will tell you, a little bit doubt I have about this reference. So I am giving you just check. Check means maybe I'm sure, almost sure, but not 100%. But this is the reference, Maurice. Okay. So this is the problem. So draw this. It's better I give you a sketch solution. Solution better. At the top, I should give a sketch. This is your problem. This is the crucible. You are blowing into this 2 mole argon. Here you have zinc liquid. Blowing, so it blows through this, and what exits from this zinc vapor, because it will vaporize plus argon. This you have to organize the gas. The temperature is, this is better I use that side, 1030 K. I am right, and P total is, this pressure is actually maybe reduced. Sorry, it is giving you 0.8 atmosphere. Not right, huh? So it is given, so I don't have to write this, repeat this. P total is 0.8 atmosphere. Start. So you follow this, what happens? Argon is bubbled through a liquid. You will let us read a study steel making. Steel making also, oxygen is bubbled. LD steel making, oxygen is bubbled through hot metal, the product of blast furnace. Then you will produce steel. Nearly steel making. Subsequently, now you are actually studying blast furnace iron making. So the product of blast furnace is taken to the steel making for final product of steel. So it will bubble through this. What happens when it bubbles? Zinc liquid will has a vapor pressure, it vaporize at that temperature, and argon, and it tries to maintain, and when it leaves under equilibrium. This is actually considered is giving equilibrium. What does it mean? It will exert the equilibrium vapor pressure. Zinc. It will not stop. It will do its equilibrium job. Saturated vapor pressure of zinc. So that and argon together will make the 0.8 atmosphere. This is when they are leaving. You have to find out how many zinc will be evaporated, or in other words, how many zinc will be left behind in the crucible, in the container. Okay, because it will evaporate. Now, for this, you need start with this. Consider the equilibrium as we write often. Consider the equilibrium. Zinc evaporation, zinc liquid plus zinc vapor. Remember to remember, I tell you one thing. 2 moles argon is not passed actually all at once. For a while. So that was 10 minutes. 10 minutes means each minute is zero point 0.2 mole. Every minute actually when it is leaving, it is in equilibrium. Taking along, okay, it is evaporating and argon together make up the 0.8 atmosphere. So you can actually consider the whole amount of 2 moles, same result. Okay, so 0.2, 0.2, 0.2 each time. So it can even reduce. You should reduce actually 1 milli in 1 second, then it will divided by 60, and 1 millisecond it's still divided by 1000. It's not so effect is same. So what will happen there actually in many installments will be equivalent to what will happen to the 2 moles alcohol. That is, it will actually take along zinc vapor, and which is, and the vapor pressure of zinc will be saturated vapor pressure that will find from the equilibrium. Consider this equilibrium, vaporization equilibrium. This is also chemical reaction. I told you phase transformation is a chemical reaction. Same principle. Okay. Only thing it is zinc either side. In so-called chemical reaction, it is different. Like metal plus oxygen one side, other side is metal oxide. It is actually zinc liquid. It's only phase different, but still it is chemical reaction governed by the second law of thermodynamics and all such things, delta G0. So delta G0 is given to you. So remember this. I should not repeat this type of things. These statements you should understand that I am talking of a chemical reaction. 118, 140 C. Delta G0 is there, minus 100.25 T joule. This is as it should be. Then what will get? Delta G0, you tell me, 1030. Yeah, that is a routine work, routine job. You get this, 14856. 14856 joule. And you substitute here minus R T ln K. K of the again same temperature. You should always tag the temperature is delta G0. K. R is, I don't have to write all the time, but still actually I have it writing ln K, or this gives you what? This leads to, let me write here better I write, or K 1030, or simply K you can write also, equilibrium constant. If you understand nothing like that, when is 0.176, that you can determine is what? Tell me equilibrium constant expression. You know what is this? Product by reactant. What is the product? Gas. So partial pressure, zinc. Okay, and activity of zinc, pure liquid. Okay, and this actually we use PZN is called PZN0, saturated vapor pressure. The name actually since this is actually term because that's pure liquid vapor pressure. Pure zinc liquid vapor pressure is saturated. So you just superscript 0, but you should this PZN. Actually, I'm writing once more so that you don't have any difficulty. This is known as PZN0. I can write for you saturated vapor pressure. Saturated vapor pressure of zinc. Vapor pressure of liquid zinc. This is how you, this is PZN, partial pressure of zinc. Ah, I have not said here delta G0. Huh. Uh, Anytime, any day, any moment. That's why another term is there. Delta G, RTLN Q. Delta G0 positive, very much possible. Okay. But delta G, you have to actually work with the delta G. Now, in certain condition, rare, delta G is delta G0. That is under standard state condition. I give you an example. Where then there delta G as good as delta G0 or delta G0 is as good as delta G0 can be positive. Positive. Only thing you can say, I tell you, okay, other than I'm telling you, the impact of delta G0. If it is 0, it can be negative, positive, anything. Delta G is standard stuff, product, synergy react. If it is 0, then what is the equilibrium constant? 1. Very good. Delta G RTLN log is there 1. So reference. Oh, delta G for any reaction on Earth or say or any planet, any other planet. Okay, 1. So when it is positive, what is the implication? Less than 1, and that you see. This you should actually see. You are getting positive or getting greater than 1. There is some mistake. Some mistake inevitable. Okay. Madam, you see, log fraction is minus, and minus plus. Coming from K's point, the log point is what? Log point anything? Negative. And this negative makes positive back there. So see, if you follow me, what I am saying, it will serve your actually 10 days book, starting books. What I am saying, equilibrium constant delta G is 0, reference equilibrium constant 1, negative greater than 1. Positive less than 1, greater than 1, and greater, and k is accordingly correspondingly greater and greater, higher and higher, and k higher and higher. Since I have started this discussion, then what is the impact of that k higher k value, higher equilibrium constant value, higher conversion efficiency means equilibrium constant is high, means reaction is almost going to the completion, 100%, close to 100%, 99% means almost gone, fully converted. That you consider in high school many reactions, okay, fully converted. And when it is less than, okay, very small, hardly any change, okay, only a small extent of conversion, and it stops at equilibrium. So these are the things. So delta G0 is actually important parameter to get the idea of the equilibrium constant. But delta G, see, small equilibrium constant, it will occur. Today's room, you have water. Today, water saturated vapor, say keep water here and come actually after 1 hour or 2 hours, this water will be evaporated away. Why? Why evaporation takes place? You see, equilibrium constant is okay, delta G0 is positive, but that's why vapor pressure is less than 1. But all the same, it will evaporate to that value. Okay, so a lot of talking is okay though. Now, so how will we make delta G negative if delta G0 is positive? Since the question is asked, actually I should not digress much. If I start digressing, I only want this term is what? Hello. This term is what? RTL and Q. This is negative. If you want to make it say positive, let it be. Let it. I'm giving you. I'm giving one example. Metal plus oxygen is metal oxide. Your favorite metallurgical reaction. And delta G0 is negative. Occurs. Corrosion. Corrosion is everywhere. You look around, you see corroded stuff. Okay. Oh, you are satisfied. Sorry, it is all negative. Delta G0, but it is not for delta G0, but for delta G. Now you understand more when you consider the reverse. Metal oxide to metal, a reverse reaction, delta G0 positive. Does it occur? Delta G0 means metal oxide to metal. It doesn't occur. Then what are metallurgists doing on Earth? They produce iron from metal iron oxide. That is spontaneous. What actually spontaneous? So at that temperature it is spontaneous. I'll make it spontaneous. Delta G, when finally delta G negativity is spontaneity. What you do, increase the temperature. When delta G0 positive, you work upon this term. Other day I was talking this term, so that it positive and this becomes higher temperature is negative, so net is negative. Higher temperature it is negative means spontaneous. Use the term spontaneous. Iron oxide is reduced. Spontaneous you mean any temperature you have to consider. Spontaneity can be applied to any temperature. So that's iron is not made spontaneously at high temperature. If you 2, 3 reduce, who stops it from being reduced? At that temperature it will reduce. That is the fate. At low temperature, this iron will be oxidized. So all are see delta G negative is spontaneous. So when it is positive, then how it could be negative? Suppose it is positive, then this should be more than that. It will be negative and greater than, numerically greater than that. So net effect is positive. And if it is negative, that is then it is actually get actual boost. No problem. Okay, no problem. Okay, but all these things actually the good question you have asked at the beginning, because this is a great confusion and many people, I should not name them, they don't take up this part. They say delta G, see delta G zero value. So you say no, I will never see. No. Delta G is the criteria. Delta G is negative, positive, so I will actually accordingly get gives the actual value. So I will make actual value such that it is actually more than this negative and more than this value. More negative than this is positive. It will be negative. So delta G0, positive, negative, actually and only initial information. On principle, stick to that. Delta G negative. I will not move from this. Then change your actually say law. Happy? And also see the delta G0. Spontaneous definition is actually isolated system. If isolated under the condition without any intervention, if it occurs actually then in isolated system. So the isolated system can start in, okay, see, I don't want to talk this. Okay. So is okay though. Then what is this value? Okay, go on. Enjoy. Is 1. Is okay though. Present this 0 what? For saturated vapor pressure. Okay, pure zinc. 0 that you can consider zinc, pure liquid zinc. It is not standard. I tell you. It is the saturated vapor pressure of liquid zinc, pure liquid zinc. I am writing. In case you have any doubt, I want to clarify this. Why 0? What is standard state? You know what is the expression? So delta G 0. So it is pure liquid zinc means standard. So hence maybe some justification. You can say, oh sir, but never make mistake. This gas is not standard. This zinc is zinc standard state. Zinc gas. What is the standard state pressure? What is this pressure? What it will be soon? 0.176. No, it is not. Solid, you see, condensed phase means it is liquid here. That is standard. So maybe that is the you can justify why is at 0. But this is condensed and saturated. This symbol. Happy? Okay. Or PZN is what? PZN is 0. Okay, right. I'm writing here in bracket. So that I work with PZN. How much? 0.176. You can attach unit very well. 0.16. Now, very good. Now, partial pressure I am writing 0.176 is partial pressure of zinc is I am writing for you. Mole fraction you know very well. NZN plus N argon. This is the mole fraction in P total. Take a look. Any mistake? Here, follow. See here, follow this gas, exit gas. Is what? It is exerted, it has attained the saturated vapor pressure and argon, and together makes this 0.8. So partial pressure is mole fraction time total pressure. What is this value? Substitute only 0.8, sir. What is the in argon? Can you tell me? Yeah. It is actually continuous. It's a continuous process. Though total is effective for 10 minutes. Total are 2 moles. So finally, accordingly, total zinc will be removed. Say 1.2 moles is a small amount of zinc. Another again small. So together is 10 times maybe. So we don't care, sir. Don't care ever. Okay, about this. But it is a continuous process. But when in living, it is attaining. What is the key? How do you know it is equilibrium? Or what is the criterion that needs to be fulfilled, or you will be satisfied? Sir, it has attained saturated vapor pressures. Who? Zinc, sir. That is equilibrium value. Saturated vapor pressure is a that is equilibrium vapor pressure. Another name of saturated vapor pressure is equilibrium. Right. These other I told you, no, solubility, saturation, soluble saturation is the equilibrium value. Their solubility saturation, it is vapor pressure saturation. Equilibrium vapor pressure. Vapor pressure of liquid zinc. So I am trying to dispel all confusions. That's maybe I think taking time though. But now it is you have no what is this too? You can solve it out, and I am solving it for you in Zn. No, the problem is very easy. Problem is very easy, and the 0.56 mole. Will you write this? And we check. Now this zinc where? This zinc where? This mole? So many moles where? This zinc where? The bomb where? This zinc mole? This is so many moles I am writing. Where? Here. Here. Or together. This zinc 0.56 mole, where it is? In the gas phase. Okay, here, saturated vapor pressure, here. Okay, here it leaves this place. Leaves zinc vaporized and liquid must have actually sacrificed that amount, or say must have allowed to have that amount escaped. So that mole escaped from this in the form of vapor and to exert saturated vapor pressure. And with argon they will make up 0.8 atmosphere. So this is one thing that you actually have. So what is that? So zinc left in the crucible. What is the question? Zinc remaining in the crucible. Hence zinc remaining in the crucible. The crucible. Tell me quickly. Easy question. I'm happy that I just over. So tell me, what is this? How many grams? Grams. All right. Let us see this question. Then now no thermodynamics. Here at least no thermodynamics. Yes, yeah, will you try? Yeah, Amartya, how much left? Right here, shall I write here? Point say in the gas phase. In case what I asked, I'm writing you for you. In the gas phase. How much zinc remaining in the crucible? This is a crucible. In the liquid form, how much? Now, so starting value of 200 grams less the mass of this moles of vapor. Okay, so the zinc of this thing. So what is this? 200 gram minus 0.56 mole of zinc means what is the mass, corresponding mass? 65.3. You know this, times 65.3 atomic weight of zinc. Atomic weight zinc. This is actually gram mole of one. You say gram atomic weight, etc. Gram mole, gram atom. How much it is? How much? See, that copper. Copper 63, easy to remember. 63.5, that is 65.3 zinc. Copper, scandium, titanium, vanadium, and copper, zinc. Periodic table. Copper, next zinc. Group 1B, 2B. Transition elements. So it should be getter. Zinc must be getter. Any question? Now, don't hesitate. Don't hesitate, please. 163.43 gram. What shall I write next? Sugolan? What shall I write next? Answer. Over. One down. One wicket down. Okay. Any questions? Okay. Ask now. Okay. So next problem 8. Okay. So you think along. Okay. And then I. Okay. Now these questions that equilibrium attainment you follow closely. I encourage that you okay you cast doubt or you seek clarification. I encourage very much. Then only you understand. So equilibrium, you see. Problem 8 now. Okay, I tell you what. Now we will consider a number of carbon burning Carbon combustion problem. Carbon combustion problem. Maybe 4 in series coming. This is so important involving problem. Okay. Involving carbon solid, CO2, oxygen gas, etc. I am giving, etc. You understand what is etc. So for this basic two relation, for this two basic data are given below. Are given below. So carbon oxygen system though. What are the two basic data? I am giving you formation reactions 100 times. What is that? For C solid, formation of CO and formation of basic data is this, or always C solid plus half O2 gas, basic data, formation data, basic formation data, formation. All the time I say, insist on formation, use the formation. C solid plus, and that formation reaction I have taught you, thermochemistry, and you should actually stick to that. C solid plus half O2 gas is CO gas. Usually, I have actually maybe twisted it. Is formation information? Amorti is not sure. Is formation? It is a formation. He is correct. His answer is correct. But can you defend why it is formation? It's one good reason. So yes, Sukolan? Product. Nothing else. Form, who form product? So that must be one, not two. If you write two, you want to make it one, 2C plus O2 is 2C. No, sir, it is not formation, it is twice as much. The enthalpy change or free energy, whatever are twice, that will be. But this is the formation reaction, delta G0. So careful. Sometimes I write delta G0, I am not writing this time, since I have written the reaction. Please follow this. Follow what I am saying, then you have all set. You all set. 700 minus 87.65 T. Then 1, this 1, okay, maybe 1, label this. Second is what? What is next? Carbon dioxide. O2 gas. CO2 gas. Delta G0 is what? Minus 394,100. 100, and then minus 0.840. No. Joule. Okay. আর একটু বড় করবো ফোনটা actually in computer I have seen actually no, this is actually size is adequate, but anyway I'll certainly, these two data I have given you. Acha, can I remove this solution? So remove this part quickly. Sorry, we have to solve 5 problems or 4 problems, I'm sorry, 4 problems in carbon oxygen, using carbon oxygen system. Start. This is the problem I'm giving to the sketch. I'm not writing the problem. Oh, problem is what? Next problem. Next we'll consider. Problem what? Tell me, what is the Q? Problem 8. 8, huh? 8. Acha. I'm sketching the problem, then you'll understand. Unnecessary writing. What is this? You have furnace. Carbon oxygen, why important? Why it is so important? Carbon oxygen burning. Why it can be important?
It is used in the
blast furnace, reference blast furnace, sir. Not steel making. Steel making is not. Blast furnace, sir. That equilibrium. So problem 8, sir. This is a this is a furnace. So suddenly I wanted to write this. Draw this. You have a this called they call this a boat or say crucible, etc. Boat. So you have carbon, solid carbon sitting here, and this is your reactor, and there is the temperature called furnace, reactor, etc. And temperature is what? First temperature I have not given. Let us say T. Let's call it. So I am not actually giving actual outline of this solution. And what is entering? You follow with me. CO2 gas. What outcomes? What exits? CO2, CO gas and CO2 gas both. This is actually, so reacts, carbon dioxide reacts, and it is an equilibrium, at equilibrium. CO gas, I'm writing equilibrium attained. Sorry, equilibrium attained. It I have to write this, or that's it. Okay, follow. Okay, temperature, pressure is open atmosphere, or P total is what? P total is what? P substance right? P total capital 1 atmosphere. What is the implication of this? It is open to atmosphere, right? Open to atmosphere. Write that quickly. Acha, since if you little bit cooperate or show actually your understanding, then I will be very happy and quickly move. So, how to solve this problem? Solve this problem, sir. What is the problem? What is the problem, sir? Sir, find right here to find PCO, or say normally we don't say PCO, percentage CO2 in the exit gas, or PCO2 will be same, will be also adequate, because from that you will get percentage. Percentage means which percentage? Mole percent. Okay, volume percent. Normally I use mole percent more than volume percent. Volume is actually for gas. We have to give the temperature, pressure, etc. Don't worry, So mole percent means mole fraction, all such thing. Don't worry. So what is your tool? What are implements to solve this problem? Think of this. You have solved how many problems? 7. You are now, okay, to some extent veteran. So how to solve? What is your in general? I'm helping you, guiding. Develop 2 equations. 2 unknowns, 2 equations. This is the first line of attack. So I need 2 equations. Can you generate 1 equation? That is about whose delta G0, I don't know. Whose reaction? First you have to write the reaction, then delta G of that. So which you must say, sir, I must have 2 relation. One relation maybe through the equilibrium. This gas has attained CO2, COC. See, equilibrium has happened where, you know? Here, say, see, follow this. Follow forever. You pretend that this still, okay, longer bed. So when it is flowing through the, maybe slowly flowing, slowly, carbon, and consider at this temperature, typically high temperature, attains equilibrium. Means equilibrium, attains equilibrium means it reaches equilibrium constant, or see strikes equilibrium constant. So follow gas with carbon reacting. So some reactions are whose equilibrium? So what is your reaction? So pertinent reaction. Let me write the pertinent reaction or equilibrium. Pertinent reaction or equilibrium, as you call it, is, let me write nicely. CO2 gas. You follow, since you are actual beginners. I'll see. Soon you will be very expert. 2 CO gas. This is this delta G0. Delta G0, CO2 plus C is 2 CO gas. Delta G0 will be what? Delta G0. You don't see? Difficulty? Any difficulty? So delta G0 you must get. Right. This is follow the formations are given to you. So you use the formation 2 delta G0, right? Very good. CO. Tell me. CO, thereupon 2 delta CO, he has said delta G0. CO, expression wise. So it will be function of temperature. I'm not writing. I'm not doing that job. Unnecessary. Function of temperature means this type of, it will be twisted. Another combination of A and B. Okay. Function of temperature. So what is this? Then you will get from this. You will get what? Delta G0 equilibrium constant is what? Using you will get, right, equilibrium constant you will get. Using what? Delta G0 is, shall I write? I'm writing. What is K? K is known. K is what? Tell me. Hey, you are yawning. You're tired, very tired, okay? PCO square, activity of gas, I'm not writing under this, we're old enough. Okay, PCO square divided by PCO2, activity of carbon. Okay, what is this value? 1. Because it's a solid carbon. So 1. And now I tell you. So this is always what you write. See, you are already They're old, but it is equilibrium, right? No confusion. Okay, so this PCO square by PCO2. Very good. So is PCO square. So hence write this PCO square by PCO2 is a knowable stuff. Known. Okay, good boy, sir. Good boy. Call it equation 1. Another equation you have to generate. So that you can solve two unknown two equations. You follow me. Two unknowns are somehow. Try at most. Another one. What is another one? What is another one? Huh? They sum to total pressure is 1 atmosphere, open to atmosphere. So, and PCO plus PCO2 is 1 atmosphere. Can you solve? Y square by x is something like that. Hence PCO is known, PCO2 is known, and this is my answer in a sense. If you want to mole fraction you know very well is actually from partial pressure, partial pressure mole fraction, you will get this X, XCO is, PCO by PCO plus, but we do this. NCO by NCO plus NCO2 though. Okay, so what is this? Moles is PCO by PCO plus. You do one thing, divide by N total numerator denominator. Multiply by pressure numerator denominator, and N by N total time total pressure is the partial pressure. Okay, mole fraction N by N total. So anyhow you can write this. It is so easy. PCO plus. I will not waste time on this so easy thing. Okay, PCO. So you know XCO is no. XCO is no. XCO is a mole fraction. XCO2 is how much? Similarly, or what you can say? XCO2 mole fraction. Two dash together 1 minus XCO, or this way either. Okay, 1 minus XCO. So what is percentage CO? Mole percent CO? Tell me. Just I am writing some first problem. 100 times XCO into 100 and percentage CO2 mole percent CO2.
100 minus
No, XCO2 into 100. That is possible. Okay. So it's a high school, below high school actually. This part I will not discuss. Okay. So partial pressure means this problem is solved. No mole percent anytime. Mole percent. So mole fraction you must know. What is the original definition of mole fraction? Moles of the species under consideration by total number of moles. Means if it is mole fraction, it is for gas, single phase mole fraction. So all gases, no solids should be considered. Careful, I cannot write so many things here. So problem is solved. Okay, so percentage problem solved. So this outline. Okay, one thing. You follow this. When you follow the equilibrium follow, CO2 gas, we are traveling over this. Reaction takes place, reaction. And it may be possible if the reaction kinetic is fast and we are fortunate enough, then it will attain equilibrium maybe somewhere here, in the middle of the path, middle of the reactor, a boat. And then what will happen? Suppose it is attain equilibrium. Fast kinetics here. Kinetic has been favorable. Okay, and the gas is flowing slowly perhaps because you want slow passage. 20 cc per minute instead of 100 cc per minute. Say, just to convince you, the equilibrium we can always write. This is equilibrium anyone and everyone can write. But how to make it feasible in the lab? Sir, you have to count on kinetics, and that depends on temperature. So at high temperature, and metallurgy is often considered high temperature system. Blast furnace. No other department talks about 1500, 1600 degrees centigrade. You go around all departments in your university, and you will see no other department. Chemistry, chemical engineering will say 200 degrees. Chemistry, likewise, 100 degrees. They have at the most an oven is there. Actually, for drying purpose. Maybe 800, okay, at times. But metallurgy 1600, even steel, stainless steel making 1700. So no one can teach us about temperature. We know. At temperature, fortunate thing is this: kinetics is fast. So it attend quickly, which you want. So suppose it has attained. I am showing you. Suppose it has attained somewhere in the middle of the path. Then after that, what it will do? Again, there is a little path left. Carbon is there. CO2 CO is equilibrium mixture. What will happen? It will pass over it. No change. It has already attained equilibrium with respect to carbon, so no more reaction. So it will just go over it. No problem. Or it may be possible it has attained equilibrium just before exiting. Then also. And if it is not equilibrium, then of course you are not entitled to write this. This equilibrium constant you cannot write. But still, in that case, thermodynamics, when say reaction has not attained equilibrium, you can get a limit from this. This is the maximum value or minimum value, etc. You can comment from this. So, but normally you are dealing with equilibrium situation. But how to attain equilibrium? This is the reason. This is how. Okay. So remember this problem. Okay. Second, 9, problem 9. Problem 9. Again, similar drawing. I'm drawing. See how I'm changing the problem. You follow me. And you have to participate. Say again, see. Any question? See. Carbon solid, again carbon solid, same. Achha, another thing I tell you in this case, this gas which has been equilibrated with carbon is called, one name is there, very popular. Last day also I talked about it, saturated solution, unsaturated. This will be called carbon saturated gas. I am writing this for you. When it is equilibrium with carbon, the gas which is in equilibrium with carbon means activity of carbon is solid carbon. 1 means, and at saturation, what is this? It is saturated with carbon solid. So what is this? Activity of carbon in this gas mixture is what? 1. So it is called carbon saturated gas. Equilibrium. When equilibrium means, other name I told you, other than a solution, equilibrium attained. Saturation means equilibrium has attained. So it is, you want water, more water? Does it help you? I have water, huh? Huh? Okay, this is called carbon saturated. This term I may use, carbon saturated gas. Okay. So if it is saturated here, why it will take up more? What will do this remaining carbon? It is already at an equilibrium. If it at an equilibrium here itself, just touching equilibrium, very good. Nothing like that. I want before exiting, you must have. The once here, then there is no scope, there is no carbon. There is no reaction. So whatever is to be done inside the in presence of carbon, in contact with carbon, physically understand. Thermodynamics, you have to physical situation, you have to read and you have to use and etc. And you have to design. So what's that? Saturated, carbon saturated gas. Another name, also called equilibrium carbon saturated gas. Remember this. This is over. Huh? So many terminology I may use later. Here again. Now changing the. I am not passing oxygen, carbon dioxide, but oxygen gas alone. Quickly, oxygen gas. Then what is coming out? Is CO2 gas? Gas. Tell me. CO2 gas, CO2, CO, and say oxygen. I am considering oxygen. So this gas, gas mixture. I should have not waste time. Okay. Again P total. Open to atmosphere. Tell me, temperature must be there, otherwise temperature T. Again, so how many unknown? You find this. You have to find. I've written here to find. Okay, this way. To find. I'm saying. Okay. Percentage CO2, percentage CO, percentage O2. Acha, I'm removing this part. This is over to okay. Unnecessarily clashing with this, so your mind will be diverted this side. Okay, over to. And 3. So what is to be done? 3 unknown. So 2. Well, tell me what is the 3? Let us see. In your Almania, which weapons are there in terms of relations, sir, involving these 3 gentlemen? So what is this? CO2 partial pressure. You consider partial. It is last job. Partial pressure, sir. Partial pressure of CO2. Very easy thing. How to get this? So 3 relation involving partial pressures. So sir, I can use here also similarly CO2. See, gas mix. Supposing oxygen, actually oxygen is very small amount though, but you don't ignore. Okay, don't ignore. Try to learn. 3 gases. So what equilibrium you can consider? See, follow these gentlemen, these three here equilibrium. There it is living. Equilibrium must have attained before it living. So here there, you think this here, an equilibrium. So tell me which equilibrium reaction you can, which reactions you can consider for equilibrium or consideration of equilibrium. Tell me. Can I write this? Tell me. Acha. It's better I ask you. Otherwise you are actually hesitant. I ask you. Can I write this equilibrium here again? So these three gentlemen, what I taught you last day's lesson, you just don't come actually for fun only. Last day what I taught, anything with anything, any you want. When I give so much freedom, you enjoy it at least. Yeah, Baba, this gentleman is very nice. Okay, he gives me freedom. Thermodynamics is a nice subject, gives us freedom. See what freedom, sir? I can consider of these three two, CO2, CO and carbon. So I can again use this. So I have to write this. Can I write? And think of others. Okay. One I am writing. So, acha, right. Write this. Consider the equilibrium. Consider the following equilibrium. What are they? One by one. CO2 gas plus carbon solid goes to 2 CO, sir. Very convenient. Very convenient. Okay. One. You work on this. KT. KT is what? P CO square. Like last time. PCO2 activity carbon, write and write one equation. This is known. Give right here known. Known means known. Okay. So equation 1. Second equation suggest
The formation reactions.
formation reactions are there. Okay, very good. Formation reaction. Any of them can do. Like say, you should have answered on a nice way, smart way. Sir, those are anything which involves oxygen, sir. Because oxygen is another unknown guy. So consider a reaction involving oxygen. So this you can consider. But I am considering this, okay? This is actually commonest. Here you see, from this, when you eliminate oxygen, you get this. This is your favorite boudoir reaction or something like that. Very favorite blast furnace. They often consider this boudoir. I do not know who is that gentleman boudoir actually. But it is actually carbon solution loss, or you see carbon gasification, many name. But you should know this by this name, okay? So I am writing, consider this following, and also consider also this equilibrium. Also this, the following, also consider the next equilibrium. What is this I am writing for you? I am not exactly not writing that. Okay, what I am writing? CO gas plus half O2 gas is CO2 gas. Actually eliminating carbon. But this is another important relation. KT, again KT. KT is what? Tell me. Again, you know. From delta G0. Delta G happen. Oh, delta G. Let us see. Delta G0. I will ask delta G0. Yes, Nirjor will tell us. What is the delta G0 for this?
PCO2.
Delta G0.
Yeah, delta G0.
You hear me first.
We don't know, sir. The equation from
No, what delta Nirjor. Delta G0 for this reaction is what? Yes, you try then. A formation. Sir, if you have not given, please bring for market. Delta G is formation of these and these gentlemen. These two are the compounds.
delta G0 CO2 minus
Delta G. And these are like in enthalpy. See how interesting that you have already learned. So why take trouble? Enthalpy is right. Chromium oxide plus aluminium is there. Delta G0 CO2 minus delta G0 CO. And what it was here? Here, see, take a look. 2 delta, understand? Is function of temperature like last time. So delta G0 to KT. To KT. 2 delta G0 is minus. Once more writing in case you have forgotten, minus RT, ln K. using KT quickly. KT is what? Yes, Amarto, KT is what? This is easy task. Get your expression. Good boy. Divided by PCO, PO2 power. Happy to? Can I call it equation 2? Is Anurag, PCO2 is known or anything of these three known yet?
The PCO2 is known.
PCO2 is known.
No. It's all.
So far, no, sir. At this stage, nothing is known, sir. We have to find them. How you are asking, sir? Your problem is over. You ask back the teacher. Sir, problem is not yet over, sir. When it will be over, I will let you know. So don't tell the teacher. You don't tell this. And what else? Yes, again, let us say again, yes, Golan will tell us. 2, but 3 unknown, 3 equation right here. And this is a good thing. 3 unknown right here. 3 unknowns, 3 equations. Oh boy. 3 equations required. Look at it. Now to 2 page. What is the third? Yes.
PCO2 plus PCO plus PO2 equal to 1 PT.
Perfect. All three together constitutes a total. Total pressure is a relation. So, and third is, and PCO plus PCO2 plus PO2 is P total is how much? Right? Sorry. Right, 1. Sorry. Let us not. Is 1. What is the name? 3 equation. 3 equation, 3 unknown. 3 equations, 3 unknown. So solve. Solve. Shall I give a star here? Star, huh? Can I start here? Where I write this problem. Start this, huh? Right here, nicely, huh? Convenient for me. Solve equations 1, 2, and 3 for PCO. Oh, sorry, sir. PCO, PCO2, and PO2. And hence percentage also you can get. Okay, it's okay though. Over though. This is no problem. One thing I tell you, just argue. Tell me, sir, instead of considering this, sir, he said this is very convenient, we don't understand. Can I use these two, sir? Two equations though. This follow. Instead of considering one, and this I'll write somewhere. Instead of instead of a double star, and I'll comment. Instead of considering 1 and 2, can I use these two? This is also partial pressure of CO2, O2, activity of carbon is 1. This equilibrium, I have said, anyone with anyone. No barrier. No, you cannot touch me. No. So I can consider. So this is actually what happens. So this is I can consider. Then you can write such like that. I can. So why are we using this? These two plus this. 4, sir. So why are you using the 5? Is it 5, 3 unknown 5 equation? What will happen? 3 unknown 5 equation? No, that means you have made some mistake. What mistake I am making? So these are manufactured from these two. They are quite independent and dependent. These are if you consider these are independent, then these are dependent. Any you can use your choice, but 2 is independent. You be careful. See, this is independent of this. Because CCO2, this is CCO2, never to be dependent. So these are mutually independent. 2 will do. Likewise, these are mutually independent. So one from this, another from that. Possible? Free, mental block, remove mental block, any. So can I double star and give this comment? Note, you could, or we could consider the above. Then you see how many are dependent and independent. I'm giving the answer 2 are independent. No more, just 2. So this say, and then these are manufactured. How manufactured? Yes, manufactured. It is eliminate carbon, then you get this. Elimination of carbon means subtraction, addition, subtraction, and eliminate oxygen you get. So 2 So only two independent, so no surprise, I will get two equations only. And third must be from the total pressure. So all set, sir, all set. So now we could consider the above two equations, above two formation reactions also. Reaction also. Uh, Reaction also. Instead of considering 1 and 2, instead of considering, okay. Okay. Also, instead of considering about to formation reaction, considering CO2, I'm writing as CO2 plus C is 2CO and CO plus half O2 is CO2. Note not only two independent reactions are available. Reactions are available in the system. Independent reaction are available in the system. And we have the liberty to consider, I'm removing all this, these are no liberty of considering any two. Considering any two of the possible four of the possible four equations for the four reactions, possible four reactions or equations. This mental block out. Okay, independent. I told you independent. Where I taught you independent. This I said you. Oh, to told you PV is an Indian state is a function of two only. If it is a given mass, two only. If it is ideal gas is a system, two only. It can be PT, it can be VT, it can be PV, but never ever PVT. Because one will be dependent. Okay, so there we use this. Okay, and likewise temperature and thermal conductivity, no, depends upon this. So mutually dependent. Yeah, so understood to this. Okay. Actually, by the way, very interesting. Very interesting. I'm giving a puzzle, easy puzzle. Class 8, class 9, perhaps. I'm removing this. It's okay though. Good boy. Good reader, sir. Remove 8, 9. Go on, sir. 10, 11, 16. Today's plan. Let us see. I do not know where you go. Maybe we'll stop in the middle. But plan is okay. We have to solve. Okay. So I cannot jump actually. I can easily say thermodynamics, okay, start from this thermodynamics T and S and thermodynamics is over. Okay, delta G is or delta G or delta O, all same, delta G or negative C, check all this. Sorry, this is actually recorded, Problem, interesting puzzle. Oh, what happens? Suddenly? Achha, maybe tired. Let it relax. For a while, maybe another one. Interesting puzzle, but you will understand this more with this. This is often an interesting puzzle, interesting fallacy. Three unknown, three equation. To solve three unknown, we know, we appreciate that we know to solve three unknowns, three equations required. You will enjoy this. I'm giving the relation then. I'm giving you the relation. 2x minus 3y plus 4z is 7. I'm giving this one equation. Another equation, 7x minus 8y plus minus 2z is 5. Giving two equations. Third equation I am giving 9x minus 11y plus 2z is 12. Three unknown, three equations. We have read this, solve this. Can you solve this? So yeah, Sukallan, you can solve. Why? 3 I have given.
If you are adding up the equation, first to the third.
That means this is no, sir. This is not given. This I know, sir. I know as much as you know. So this is a dependent one. Manufactured. Again, if you consider these two independent, then this can be manufactured. Concept of manufacturing. So, but this is the wrong guy. This is a dependent one. And the third, this one, this is a dependent one. Hence, obtained by addition. Obtained by addition. Obtained by addition. I am writing. You understand this. So, can we solve? So, can never be solved. Hence, cannot be solved. Hence, x, y, z can be solved here. So, effectively, how many equations are given? So, this will clarify this part also. This example, everything will clarify. So, that's why in the class, actually, I often ask this question. Or later on, phase rule also. Can I remove all these things over? Problem 10 now. Move on to problem, keep line. So, I am removing this. Okay. So, where I am removing this. It is better. This is so easy. Let me remove this. Please. Problem 10. Now, you participate more onto this. Problem 10. What it is, sir? Again, follow. I said in a series, I am considering this is carbon burning. Again, carbon bed, carbon solid. What I am passing this time, oxygen and argon mixture. Oxygen is to argon. To gas I am relating. And what is the ratio? Is since I have actually designed this, 2:1 maybe. 2:1. What is the temperature? Temperature is T, sir. We are not solving any problem. Outline of the problem. We are giving the outline of the problem. Okay. So shall I write somewhere? Okay. What exiting? What exiting? Tell me. CO2, O2, like before? Like before. So previously 3 unknown, 4 unknown. So what is equal? 4. Let us see, develop. So 4 equal. So in this case, note we are giving the outline. Note we are giving here the outline of the solution. So that no one can be disappointed. Okay. So quickly. So in this case, 4 unknown. 4 unknown. 4 unknowns. Write this PCO, PCO2. Write this PO2 and P argon. Happy. So 4 equations required. And which equation? Dependent type. Independent. I'm sorry. Independent. 4 equations required. What are these? I'm helping you. What I'm telling you? The previous 3. So previous 3. So use the previous 3 of 3 equations of problem. Tell me 9. And good boy. So one thing, only 4th equation, sir. Total pressure utilized, equilibrium utilized. You cannot involve argon through reaction. Can you involve argon through reaction? It's an inert gas. Diluent, we say. Okay. So you use this. You use this. This is the first time you are learning. First time. Use this. So another equation can be obtained this way. So the fourth equation can be set up this way. Fourth equation can be set up following way. In the following way. Happy? In the following way. Quickly. I am writing something. I can now. This is not needed. These are not needed actually. These are not needed. So 3 is the 4th I am showing. NO2 by N argon. Right? Follow this. This logic you use this. Inlet is NO2 by N argon equilibrium. What is this? From mass balance. You say from mass balance. From mass balance. Oxygen will not be destroyed, neither argon. Carbon, okay. So oxygen. So NO2 by N argon will be same, okay. So NO2 by N argon at the inlet, how much? Tell me. 2:2 means 2. 2. Equilibrium. So this at our interest is where? Now that is fine. Where? Which one? Here, this or this? Equilibrium, sir. We are considering these are at equilibrium, right? For unknowns, at equilibrium, right? Again, you always see the equilibrated gas, right? Always right. Equilibrated gas means you have to assume that this when it is going over the bed, carbon bed, it is attaining equilibrium before leaving the reactor. So from mass balance, how much? Now this actually you have to write. Follow this. This is new to you, but the first time. I mean, oxygen is balanced. See, the oxygen that you put in is where the putting has what? Oxygen is where and where and where? In CO, in CO2 and O2 itself. So let us write NO2. I am writing. So suppose NCO. Achha, suppose NCO moles of CO. PCO means NCO moles of CO. So how much oxygen is there? O2 is there. Achha, 1 mole CO. Logic. Important. Whole life. 1 mole CO is giving how many oxygen? 1 mole. 1 mole CO is equivalent to how many oxygen? Half mole O2. This logic you know. Half mole O2. So this is actually so NCO mole will be okay. It will give you NCO from NCO you will get how many moles of O2. So half as much. What I am saying, moles of half moles of O2, half mole of O2. So CO gives half as much. So NCO gives how much oxygen? NO2 half as much. That will be NO2 moles half as much because one. Okay, follow this. 1 mole CO. Okay, 1 mole of CO actually contains half mole O2. 1 mole of CO contains half mole O2. Carbon is there, but O2 wise I'm talking. Half mole O2. So how many moles are here? This is PCO. PCO2 means NCO. Corresponding values are NCO. NCO moles are at equilibrium. NCO, shall I write here? NCO moles at equilibrium. This is at equilibrium, right? NCO moles of CO. NCO2 moles of CO2, and so on. Okay, like this. NO2 and N argon. So now, at equilibrium. So NCO moles of, okay, how many accounts for how many moles of how many moles of O2? So this is actually 1 mole, half NCO. Okay. So NCO moles of CO half times NCO O2, and I'm balancing O2. I'm balancing the numerator. I'm balancing mass balancing O2. So NCO moles 4. This is 4. So how many O2 is there? If 4 moles of CO say exit, answer. So how many moles of O2 there? 2 moles. The half as much. So I have written half as much. Plus NCO2, shall I? Oh, 1 CO2, 1 O2. Plus oxygen, 1 O2. Okay. So 1 mole CO2 right here. Equivalent to means it gives 1 O2 or 1 O2 obtained from 1 mole CO2, etc. And what is argon? Right again, equilibrium. These are equilibrium configuration. Quickly, since you know this N can be converted into partial pressures easily. I'm writing this, but this is the first time I will write, and I will not write later. PCO2 plus PO2 by P argon. Right? How will you get this? If you ask me, sir, how do you get this? By I'm writing by multiplying. Oh, by multiplying both numerator and denominator. Easy. This is so easy. I should not write this. Explain this by what you know. How to get partial n by n total is the mole fraction times total pressure. So P by NT. P by NT. Top, bottom, numerator. P by NT is what? Follow. P by NT. PCO by NT. NCO by NT is what the mole fraction. times partial pressure. Times pressure. Total pressure is partial pressure. Okay, you are not feeling well today? Huh? Tired, na? Looks tired. Okay, it's okay. Everyone very tired. Okay, okay. It's okay though, na? This part. So anytime I get, I will not write actually no. I will, to save time. P replaced by P. So what is this? This is which equation? This is which equation? Can I remove this? Call this equation. Call this equation. Call this equation. Fourth equation. The fourth equation. So now solve for say over. So what you are getting here? Half PSU2. So what you are getting actually? That is I'm written so I should not. This is actually you can get this. So it is equation after all. Equation, so many equations. So you write actually hence solve equations 1, 2, 3 and 4 for tell me NCO PCO sorry PCO2 PO2 PR1 over. Okay, answer. Answer. This is the solution. This problem 10 is over. Is okay? Any questions? 11. No, you don't have any questions? Okay. Still take more time. Only 11. Okay. Quickly. Now, this problem, can remove all these things excepting these two. This is the last of this carbon oxygen series. Okay. Then I'll take up another one. How much time? No, no. Yeah. No, how much time is? It looks, you came actually 5:30, 6:30, 6:30 and 7:30. 1 hour. 7:30.
Around 7:40.
Now, you came 6:40, 6:30. 70 minutes gone.
Yes, yes.
70?
1 hour 70 minutes.
17, 17, 1 second. It's okay. Don't wait a bit. This problem follow this. Remove this, remove. Can I remove this? Okay. Relax. Okay. Maybe this figure I will not. Problem 7 I will write perhaps. This is language I will write. Let me remove this. I write problem 7. Problem 11. Sorry. Start. Writing this. Okay. Carbon is burned. Now this time this is a full-fledged problem. Carbon is burned. Burned is burned with pure oxygen. With pure oxygen to yield a combustion gas. Let us go fast. To yield a combustion gas. Burn means combustion gas, that is with a log PCO2 log PO2 of 10 to the minus 14 of minus 14 okay, or minus 14 at 1300 Kelvin. Happy? How many moles of carbon are burnt per mole of oxygen per mole of oxygen used. Oh, that data I have removed this, but I am writing this. Don't worry. PT is unknown, right? PT is unknown. I am very sorry that I have removed that data, but since we have already done this, okay, C plus O2 delta T0, start solution. Oh, sketch is necessary. Again, as before, similar carbon solid, and here you are sending oxygen gas, pure oxygen, and it is leaving. What is this leaving? CO, as we expected, CO2. Obviously, CO2. What else it will be? CO2 and oxygen gas I would say what is the given here? Fortunately, is PO2 is given 10 to the minus 10 log PO2 minus 14. Log PO2 is minus 14 means PO2 is 10 to the minus 14 atmosphere. This is gas mixture CO2 oxygen gas. This gas mixture has PO2. Okay, is minus 14. So PO2 is 10 to the minus 14. Okay, so this is called. This is if you are interested. This is called oxygen potential. The important parameter, the chemical potential of oxygens. Chemical potential I have taught you. Partial molar free energy, mu, etc. This is called the. But I'll touch upon this later on. Oxygen potential, carbon potential. When we will discuss Illingham diagram, this is called the called the oxygen potential. Oxygen potential of the gas mixture CO2 O2 etc. Equilibrium value. So this is also called. So this what is the you have to find. I write this. What you have right quickly. Consider the following to equilibrium. As you know, consider the following to equilibria. Quickly. I wrote the but it is for completeness right here also. C solid. I'm sorry. Go slowly. Half O2 gas goes to CO gas. Once more write delta G0 I wrote, but I have removed this minus 11700, you know, minus 87.65 T joule, and another is C solid. I'm very sorry. Oh no, it is written there. Oh, what stupid thing to do. It is already written there. Right hand side. It is saved. The following to equilibrium. No, following equilibrium. Which equilibrium? Equilibrium. I'm writing. You follow with me. CO gas. That one. You are familiar with this already. This equilibrium I am considering. You have to follow one thing, interesting thing, that this time don't consider CO2 plus C is 2CO. This gas mixture has not attained equilibrium with carbon. It should be written. Note, this is not giving the problem, but I am helping you. Note, the exit gas does not, underline not, come to equilibrium with carbon. With carbon. So it does not attain that equilibrium. I mean, that equilibrium is ruled out. You cannot consider. This is possible. That means in previous cases, if it is not mentioned, you have to consider that it is coming to equilibrium. But if it should be mentioned here that it is not coming to equilibrium, or even if it is not mentioned, you will understand indirectly. Follow this. So that equilibrium is not considered. So maybe this equilibrium is what you know, the CO2 O2 gases say not equilibrium with carbon, but CO2 they are having their own equilibrium. So living here, since it doesn't depend on carbon, it is not equilibrium with carbon. So when it is out here, you also maybe trying to establish an equilibrium. What equilibrium? CO2 can attain an equilibrium, and it is by this it has meant that it has attained an equilibrium. At equilibrium, what is the partial pressure of oxygen of these three? 10 to the minus 40. Utilize this value. So these reaction consider the following. These reaction attended. So not the CO2 plus. Note here. Right. Note here CO2 plus C. CO2 gas plus carbon solid goes to 2CO gas. Note here. The reaction does not attain equilibrium. So we don't use this. So we cannot use this equation. So we can't use this equation for the solution. In the solution. Okay, etc. In the solution. In the problem. So, but this is follow this gas mixture actually in terms of CO, CO2, O2, this is equal, as it says, it is equilibrium value. Oxygen potential is equilibrium PO2, right? Oxygen potential is I am writing here, since oxygen potential is activity of oxygen, just at equilibrium, right? At equilibrium. This is the answer. Oxygen potential of a gas, oxygen potential of a gas mixture is activity of oxygen. What is the activity of oxygen? Tell me. You know. The next moment, activity of gas is CO2. So hence PO2 equilibrium. So, oxygen potential of a gas mixture, or maybe other also, okay, of a gas mixture or system like I'm writing it, or system like interesting. This is your very important term in blast furnace and steel making. MMO2, metal oxide, oxygen involved. So this, or a gas mixture or system like MMO2. Enough. Equilibrium value, activity, hence is partial pressure. This is. If you ask me, sir, how do you relate with the chemical potential? Chemical potential was GI bar. Mu GI bar. GI bar is GI 0, RTL and AI. See, coming. GI bar is, I should not actually digress so much. GI bar is, but I just touch upon this. There is little bit difference. GI bar is the partial, it is the chemical potential. Partial molar phenol generous chemical potential of I. Chemical potential of I, of the species I. I may be oxygen here. But then you have a difficulty, sir, GO2. It is not RTL and AO2, but you are saying AO2 only. Difficulty. If this is the oxygen potential, chemical potential oxygen, but this should, you have said it is purely AO2, but here it is there, but with RT, and not only that, GI 0 plus RTL and AO2 shall. Then you have to distinguish between this. This is GI bar. This is also known as, symbol is another common symbol, mu. GI bar. There are others also. Is anyone offhand can remember what is GI bar? GI bar is okay, fine. Name, symbol. What is GI bar? Name is partial molar energy. What is that? dg prime dni under constant temperature, pressure, and nj, nk, etc. all constant. This is the total definition. Then why I said, no, if you add dn moles, then change the ratio. This I said. I should not write so many things. I will go back. I should not go back at all. I spend a lot of time because this is after your regular class. Yeah, here. Okay, okay, this special class. So good boy. So distinguish this. So I am not saying chemical. It is oxygen potential. Similarly, carbon potential is there. Okay, when oxygen potential, there must be oxygen must be present in the system. Enough is enough. So consider this equilibrium. Okay, he says, I'm giving you. See, I'm not hiding from you. I'm not tricking you. I am giving you that there is this gas mixture. This is not in equilibrium with carbon, which is not a carbon saturated gas. As I said, carbon saturated equilibrium with carbon means carbon saturated, not a carbon saturated gas. Right, that also not a carbon saturated gas this time. Shall I write? Not a carbon saturated gas. Right, right. This is an example why it is not saturated. Not a carbon saturated gas. So because it is not in equilibrium with carbon, its activity in carbon is not one. It's okay. But all the same, they have struck equilibrium, and the oxygen potential of PO2 equilibrium is this way. Okay, very good. Can I proceed now quickly? So again, but question is little tricky. How many moles of carbon are burned per mole of oxygen? You see, the question pattern has changed. Previously, what is the partial pressure of CO, PO? Three unknown, three equations, two unknown, two equations. So K. What temperature, Baba? What temperature? Achha, here I will help you. Delta G0 quickly, since I am using the data. Or delta G0 is, tell me what? Tell me what? Minus 282 400 plus 86.81 T joule. So quickly. So delta G0 1300 as you should consider. Oh, temperature I have not said. Yeah, give a temperature. Furnace is running. Furnace, metallurgical furnace. Very hot. You know, where the oxygen was lancing in a ladle. Okay, you know, it's still going out. stainless steel. And so some sparks actually came up and then they fall down here. I was working there. I was actually there training, graduate training. Bihar Alloy Steel Limited, Patratu. And see what happens, 1600 degree, liquid solidified here. Delta Q 1300. See, your thinking, sir, heavy, sir, AC room, so heavy job. Delta Q 1300 is minus 169,550, 169,547 joule. Okay. So what is the K? Is minus RTL, right, minus RTL and K 1300. R is 8.314 and T is what? 1300 itself, or K 1300 turns out to be is 6, big value, 6497226. Happy? No happy? Not is what? Give the expression now. Give the expression now. Tell me PCO2 by PO2 power half. Happy? Equilibrium. I'm very sorry, getting clumsy. So I'm very sorry. Okay, is what? Right. PCO2, PCO. What is the PO2? 10 to the minus 14. 10 to the minus 14 to 10 to the minus 14 and half is 10 to the minus 7. Now it will reduce. Okay. So PCO2 by PCO is what? Or PCO2, oh, sorry, go slow. Actually, PCO2 by PCO is how much? Sir, is I am writing NCO2 by NCO is 0.65, is 0.65. If you solve this, NCO2 by NCO. Now you see, now smart way to solve this. Which one? Which NCO2? Which NCO? Where is this? This are where? NCO to NCO, where it is? PCO2 by PCO. This is where applicable here. These are equilibrium means here. I am considering this equilibrium. So here NCO2 moles are there. NCO moles are there. Corresponding pressure PCO2, PCO, and NO2 and PO2, etc. Is okay though? Now you see, you have to, now what is the question? I am writing a smart way, smart solution. Now NC by NO2. See, I am solving the question. How many moles of carbon burnt? Suppose NC moles of carbon burnt or N mole of oxygen that you have input. Okay, moles are not given here. How many is not given? Per. So NC by NO2 is the answer. Carbon burnt per mole. The smart way of writing the answer, or I will give a simpler way, so that you can, okay, when you can do the simpler, then you will be very smart. Follow the NC by NO2 is what? What is NC? Carbon balance, mass balance. What is C? C reports where? NC. C reports where? As CO2. Good boy. NCO plus NCO2. And NO2 as what? Tell me. NO2. Again, see the gases where oxygen is there. The oxygen is not here. See, oxygen is not withheld by carbon. Carbon does not do that. Okay, it doesn't take that. So all are coming out. So NCO2. Tell me, NCO is half NCO, 0.5 NCO, same reason, plus NO2. Now here I make a simplification. Is NO2 so small? You have seen the pressure, 10 to the minus 14. So negligible. This I'm, if you don't neglect that, I will also tell you what can be done. At the end, you will remind me of that, sir. If oxygen is not negligible, sir, or you don't want to consider, even if it is negligible, I don't want to consider. Such is the spirit. Now, sir, I don't want to consider. Let us solve this. NCO2, follow this. I'll go to the top. Ignoring NO2, which is small. Now go to the top quickly. This part I can remove easily. This part I can very easily remove, na? Or quickly. Or NC by NO2. This is good idea. Give a star and star here. Go slowly. NC by NO2. Just tell me how to write this. What you have here? You please follow. NCO2 by NCO from, call it equation 1. Call it equation 1. 2. NCO2 by NCO is what I am writing. 0.65 NCO and 1 NCO. So NCO plus all cast in terms of NCO, all NCO will cancel out. Answer is what? Answer is what? NCO is 0.65 NCO. And then you write here NCO2 0.65 NCO is here from equation 1 and 0.5 NCO plus what is the answer? 1.65 by, tell me, 1.15. This will be, if you do this, then it will be 1.43. And what I'll write next? Answer. So how many moles of carbon must be burned per mole of oxygen? Sir, 1.43. It's okay though. Shall I repeat this? This okay though. This is equilibrium, one equilibrium only I consider, and with the help that oxygen is 10 to minus 7. Alternative route, and lastly I'll tell you, sir, I don't want to ignore, sir. At least once in a life, you show us. Show us or give us clue. I will give you clue. I will not solve this. Okay, I have solved this. Okay, equation I can generate, but I can give that. That will be good enough. So that is good enough. Alternative procedure, simpler. Alternative. Since you say, sir, I was not so smart, sorry yet. Alternative was simpler procedure. Simpler procedure, quickly and short, very short. Let carbon, moles of carbon are burned per mole of oxygen. Let how you get this? Okay, let n moles. Let n moles. Let you answer this. Let n moles of carbon burnt just as the as per mole of O2 introduced. Okay, per mole of O2 passed. You just are answers. N answer. So do this. So carbon balance. So you don't go by ratio individually. Individual carbon, oxygen. So carbon balance, right? Carbon balance. What is carbon balance? N is what? Tell me. Carbon burnt. What they go? Exit NCO plus NCO2. That you see. CO has no number. NCO. Number of moles. NCO because 1 is to 1. NCO2. Leave it there. Then carbon balance. And oxygen balance. Oxygen balance. Tell me. Oxygen balance. How? What is given? Per mole. So 1, sir. 1 or 2, okay, 1, let me check. It's okay. Well, it's okay. Okay. 1 is what? 1. So, how many? So, yes, I can do the same balance. Right that 0.5 NCO. Write that NCO2 plus NO2 and right here itself negligible, sir. Negligible once more. Negligible. Sorry. So, this. But this is. I'm very sorry. I've removed that paragraph. What is the NCO? But recall what is the NCO2 by NCO? That was that value. Tell me. NCO 0.65. Recall that can 0.6. I have this value. This 0.65. This I have removed. But this relation is there. 0.65. Use this. But here use what it is. Tell me what it is. 0.65, 0.5 NCO plus 0.65 NCO. Sorry. 0.65 NCO. What is this? 1.15 NCO. 1.15 NCO. Okay. Or NCO is how much? Or NCO is, tell me, 1 by 1.5. What is the NCO2? Tell me, Aja. 0.65 by 1.15. Then what is the N? Carbon bond. Let N moles carbon bond. That is your question. For one mole you have already used here on the left hand side one. So what is the carbon? N is nothing but, sir, NCO plus NCO2 is nothing but 1.65 by 1.15. Exactly the same answer. Is the 1.43, sir, if the answer. Same answer, right? Same answer. I tell you what, the concluding part is this, that note, comment, additional comment. If pressure What is this called? If PO2 is not neglected, even though small, if PO2 value, even though small, or say it is appreciable, finite, okay, or say, if PO2 is not neglected, that is best too. If PO2 is not ignored, then how to solve this problem? Then how to solve this problem? Question, put the question. How to solve the problem, this problem? I am telling you something. Then what you must know, here, how to solve this problem. You know, another unknown brought in. You can, O2 is there all the time. So another equation is there. And what is this? See, something is missing. PT must be known. If PT must be known, like the total pressure can be, it is, though moles I have solved, but it can be shown actually. So can be, in that case, answer. In that case, this I solved actually here. It is already solved in that case, but I don't want to take up this much. In that case, P total must be known. So this is okay. What this problem is problem 11. Okay. Now are you tired? Then I will stop. Then. Okay, leave it there then. But a lot of problems are remaining. Actually, 16, still 5 problems. Okay. I thought at least another problem I will solve. But anyway, 12, 13. I thought, then another. But anyway, if you are tired, then it is no use. Unless you enjoy, what's the use? So okay, over. Okay. So can I hear this? Stop this? How many times?